All right, this video is meant to help us understand how to use the sums of powers formulas, such as the one up top here. We've got the summation of the I cubeds. And basically these formulas are to help us save us a lot of time. A lot of times when we're doing these summations, we're taking them from terms 1 up to maybe term 40 or 50 or 500, and we don't really want to find those term by term. Well, the nice part about the summations of powers, so I to the first or second or third, is that a lot of them have some really good shortcuts, like this formula up top. Now, we'll show you how to use them here in just a minute, but at first we want to understand where they're coming from. And the way to prove them is using what's called mathematical induction. Mathematical induction basically is the idea of dominoes. It just basically says, if you can guarantee that the first domino will fall over, and then every domino will knock over the next domino, then these summations of powers, if they work for the first term, such as if we plugged 1 in for both the basic I cubed, so 1 cubed being 1, and plugged 1 in into what supposedly is the shortcut, right? N squared, n plus 1 squared over 4. So notice I plugged in 1 for n in that first formation and basically ended up with 1. Well, if it works for the first term, right, it worked in the basic idea of the summation, it also worked in the shortcut. Now all I need to do is prove that if it works for one term, it'll definitely work for the next term. Right? That idea of dominoes again. If one domino falls and we guarantee that it'll knock over the next one, then we're guaranteeing ourselves that this will just work forever for any 1 up to n, right? N terms, for n number of dominoes, if you will. Well, induction basically says this. If you take S sub k, so that being our formula up top here, right? 1 cubed, 2 cubed, 3 cubed, all the way up to k cubed, that should be equal to our shortcut formula. We're going to assume it works. But if it works for k steps, we need to prove that it works for k plus 1 steps. So notice I took k squared, it became k plus 1 squared. K plus 1 squared became k plus 2 squared, right? Then the next step in the sequence. Well, what we need to prove is, again, if this is supposed to be k plus 1 summation, right? Or the summation of 1 to k plus 1. Well, is that a true statement then? Well, the first thing we're going to do is rewrite our initial statement. 1 cubed, 2 cubed, 3 cubed, up to k cubed. We know those are true. So we need to know, does it work for the next step, k plus 1 cubed? Well, doing a quick little bit of algebra, if we know it works for the first k cubed steps, we can substitute out k cubed, or 1 cubed through k cubed, right, for our formation up here. So notice I just took out what we assumed was true, right, this much in our sequence there, and we plugged in what we assumed that was equal to, k squared times k plus 1 squared over 4. Then it's just a matter of doing some algebra. We need to prove that this statement would give us the statement we have right here, this k plus 1 squared, k plus 2 squared, all over 4. Are these two things equal? And what I'm going to do is go ahead and do a common denominator first. And at the same time, I'm going to realize that, hey, there's a k plus 1 squared in this first fraction. And technically, if I separate this cube, there's a k plus 1 squared in the second fraction. So I'm going to take that k plus 1 squared, and I'm going to factor it in front. Note the 4 on the bottom, right, common denominator. And I've got that k squared, and the 4, and the other k plus 1 still left behind when I factor out k plus 1 squared. Then with a little bit of factoring, right, distribute our 4 first, and then factor k squared plus 4k plus 4 into k plus 2 squared. I get the statement, right, just like we had previously. This statement here, or our initial statement here, will be equal to, right, our statement there. Or basically, as we say in math, QED. We proved what we wanted to prove. These formulas are going to work for the first step, and they'll work for every step after the previous step. So if the previous step worked, I guarantee the next step will work. That means our formula not only works for I equals 1, but it would work for I equals 1 up to whatever number of steps we want. Again, that's just a quick little intro to induction. Now, the major idea of your assignment, more than likely, is going to be how do you use these? Well, combined with a couple of other shortcuts that we have, we can use these formulas anytime that our summations look like a polynomial. So you'll notice down here we've got 1 through 10 for 4i squared plus I minus 6, right? The summation of all of those terms. So I'm going to use a couple of shortcuts that we've learned previously. I'm going to separate my summation. I'm going to take the sum of the 4i squareds, and at that same time I'm going to factor out the 4. I'm going to take the sum of the i's in the middle, and I'm going to take the sum of the negative 6's on the right. Well, I squared, as you notice up top in the middle here, has a nice little shortcut, similar to the one we had on the previous page for the I cubes. I alone is this first one over here. Sum of the i's is the number of terms times the number of terms plus 1 over 2. And finally, the last one is just a constant. We've got 10 terms, but they're all just 6. There's no I in the formula, so I can't plug in 1 or 2 or 3. Basically, I'm just going to get 6 every time. Well, let's take out our I squareds and let's plug in our shortcut formula here. The sum from 1 to 10 of I squared is really 10 times 11 times 21. Notice I just took out the ends, I plugged in the fact that there were 10 terms, and again, we're all over 6. Don't forget that 4 in front from our actual problem here. Then in the middle, like we said, it's 10 times 11 over 2. In the middle, the I to the firsts. And finally at the bottom, negative 60, being, like we said, all terms of 6, but 10 times over. If I just do a little bit of arithmetic and add those up, we'll get our answer. Now, the one trick to these formulas is you'll notice that each one of them starts at I equals 1, I equals 1, I equals 1. Remember when we proved that formula previously, we proved that it worked for the first term. Well, these formulas assume that we're adding up all the terms starting from 1 up to n. So what do we do about this formula down here? If it says we're starting at 5, going to 100, if I add up all of the terms using my formula, it's going to assume that I had terms 1, 2, 3, and 4, as well as terms 5 through 100. Well, the easy way to do that is let's break this into two pieces. Let's think about those terms from 1 to 100, but then let's subtract off the 1 through 4, the 4 terms that we didn't want. And in that case, I can still take advantage of my shortcut formula. I can take my formula for the first 100 terms, minus my formula, right, n squared times n plus 1 squared over 4, for the first 4 terms. So let's plug in 100, and we'll plug in 4. Again, we'll figure out what both of those come out to. We'll do the subtraction, and you'll notice that is 100 terms of cubic terms. So actually, technically, we took off 4 terms. There's 96 terms of cubic terms. It's going to be a pretty big answer. So again, notice how that worked. But the nice part was I didn't have to find all of those terms, 96 different numbers. Instead, I could again do one formula for the first 100 terms, then do one formula for the first 4 terms, and take away those first 4 terms that I didn't want. I hope that helps you understand how to use the sum formulas. Again, if not, I would rewind a little bit, maybe go back over these 2 examples. But as long as your summation, your sequence inside your summation looks polynomial-like, you should be able to sort of break them apart, as we did in the first one, maybe do a little factoring, and then you should be able to use your shortcut formulas given to you up top here. They're also given to you in your book, and they're also likely given to you on any worksheets you might do. But again, take advantage of those formulas and see if that helps you out. If not, make sure you talk to your teacher, ask lots of questions. Good luck, and happy summations.